So let's talk a minute about vision. So how we see different things. I don't expect you to remember the different parts of the eye, but just wanted to explain it for a minute. So the cornea is the outside surface. So on the right side here, this outside surface of our eye is called the cornea, and that's where most of the light refraction occurs. That's because the light is going from air, index of refraction of 1, into a liquid surface, So it's called the aqueous humor first, then the light will go through the lens, and then vitreous humor. They're liquids of sorts. Because the index of refraction isn't as widely different between these fluids and the lens actually is primarily responsible for the fine-tuning of our vision, being able to see farther away, closer up, but the primary refraction is done by the cornea. Now, everyone has what is called a near point and a far point. The near point is the closest something can be to see clearly. So if you hold up a paper to read the words off the paper, how far do you hold that from your face? That's your near point. The far point is the farthest away something can be to see clearly. These both change as time goes on. When we're young adults with normal vision, if that is the case, our near point is typically around 25 centimeters. Our far point, we say, is roughly infinity. Now, granted, I can't see a road sign in, Tooele from Salt Lake. So infinity is really pushing it, of course. But that's what we assume as we start thinking about our equations that relate focal point, or focal length, I should say, to object distance and image distance. If we are not able to see clearly far away, so not able to see clearly far away, I need glasses for distance. I'm fine walking around my house, looking across my room. I'm fine at work walking down the hall, but if I saw someone down the hall quite a ways, they'll be a little bit blurry. I won't be able to read the room numbers from far away. We call this, well, I should clarify. If I can not able to see clearly far away but can see up close, fine. We call this nearsighted. Another term for nearsighted is called myopia. Just in case you care, you don't need to remember these words. Ultimately, when we are looking at different things, these ciliary muscles that surround our lens in our eye change the radius of curvature of the lens. And that's how that fine tuning and fine focusing is done. As time goes on, our lens becomes less pliable and we cannot focus as well as we used to. So ultimately, what happens in my eye, as we can see here, here's an object we're looking at. Here's the image created on our retina. Our retina is our screen that we look at, that the image forms on. If I'm nearsighted, as light comes into my eye, this light coming in focuses too soon. Now, this is highly exaggerated, but as the light comes in, it ends up creating an image that is in front of the screen. And so by the time the light passes and gets to the screen, it's blurry. It's not a clear, fine image. So what I need to correct this vision is a diverging lens. So as the light comes in, it goes through the diverging lens first, which spreads it a little bit, and then my eye finishes the focusing onto my retina. So diverging lenses are needed to see far away if I need help with my vision, which I do. Those diverging lenses cause the light to spread out a little bit, and then my eye can finish the focusing. The point of the diverging lens is to take an object essentially infinitely far away, so a far away object, and create the image at my far point where I can see it clearly. This is what the lens is to do. Now, if I go to the eye doctor and I get my lens prescription, it's listed in diopters. What diopters means is 1 over the focal length, where the focal length is in meters. So my prescription is going to be negative because diverging lenses have negative focal lengths. And then the number of diopters is going to directly relate, or I suppose inversely relate, to the focal length that I need. So just the help we get from the glasses. If we're not able to see clearly up close, far away, okay, we call this farsighted. It's called hyperopia. So in our eye, as this light comes in, our cornea and lens together actually don't focus the light fast enough. Or soon enough as far as length goes. And so by the time the light gets to the retina on the back here, it still hasn't completely converged together to create a clear image. And so we would see blurry images. Someone that is farsighted needs reading glasses, essentially. Reading glasses are converging lenses. So as this light comes in, the lens starts to converge the light, and then your eye can focus it on your retina. So converging lenses. The diopters is still the same in terms of meaning. If you need reading glasses and you actually get a prescription from an eye doctor, they're going to give you a prescription for some positive value because it's a converging lens. And then the numerical value is going to relate to the focal length you need. The purpose of your reading glasses would be to take an object that is at a comfortable distance from your face. So where you want to hold say a book, you're reading a book, where you want to hold that, the distance from your face you want to hold it. The purpose of the glasses is to create an image where you can actually see it, which is at your near point. As we get older, eventually we need reading glasses. That's just a general rule, or not rule, but a general fact. If you have adults in your life, like parents or grandparents, and if you ever notice them reading, you might perhaps see that they hold a book or paper farther and farther away as time goes on. And that's because they're developing this hyperopia and their near point is changing. That happens to all of us, not all at the same rate, but it does happen to all of us. Let's look at an example problem. So a nearsighted person cannot see clearly beyond 25 centimeters. What power and type of lens is needed to correct his or her vision? Okay, if I cannot see clearly beyond 25 centimeters, that means my far point is 25 centimeters, which that's not very far, so this vision isn't all that great, but that's okay. We love glasses, contacts, that sort of thing. At the far point, this is where we want the image to be. So we want to be able to look at an object really far away, but be able to see the image of it at this 25 centimeters. So essentially, we want S to be infinitely large. S prime is going to be negative 25 centimeters. Why negative? Well, if we think about diverging lens that we're looking through, so here's our eyeball. That's a kind of a scary picture. Anyway, our eye. If we're looking at something really far away, but we can only see it clearly up here, we just need it to be closer. And really with eyeglasses or contacts, the images are always on the same side of the lens as the object. If it's on the same side with lenses, that means it's virtual. And mathematically, that means we have a negative S prime value. All right, so as far as the power of the lens goes, the power is 1 over F when F is in meters. The units are these diopters. So 1 over F is what we're looking for. In this case, we want S to be infinitely large, really far away. So this term is going to go to 0. So 1 over F is going to be simply 1 over S prime. So we want S prime, we want the image to be at negative because it's virtual, 0.25 meters. I need this in meters for this to be diopters, which is what we call the power of the lens. We need a diverging lens to bring that image closer to us than the object being far away to create an image closer to us that we can see. A converging lens, when they're used as glasses, reading glasses, create their image farther away. So diverging lens is what is needed.